Have you ever just stopped and wondered how your phone or your computer actually works? I mean, it seems insanely complex, right? But what if I told you that underneath all of that, everything is run by just a handful of really simple, really elegant rules?
So that's what we're going to do today. We're going to peel back all those layers of complexity. We're going to look right past those crazy-looking circuit boards and get down to the basic, fundamental principles that tell every single electron exactly where to go and what to do. Here's our game plan. We'll kick things off with Ohm's law, the golden rule. Then we'll see how to string resistors together in a series. After that, we'll get into Kirchhoff's law. I'll show you a neat little shortcut called the voltage divider, and then we'll put it all together and solve an actual circuit. Okay, let's dive right in with the absolute bedrock of all circuit analysis, Ohm's law. Seriously, if you can get your head around this one concept, you are well on your way.
Okay, that sounds a little academic, right? So what does it really mean? Let's break it down with an analogy I love, a simple water pipe. Think of voltage as the water pressure. You know, how hard the water is being pushed. Current is the actual flow of water, how much is moving through. And resistance? Well, resistance is just how narrow or wide that pipe is. So Ohm's law is basically saying that if you want more water to flow, you've got to either crank up the pressure or get a wider pipe. Simple as that.
And this right here, this is the famous formula V equals I times R. Voltage equals current multiplied by resistance. It's such a simple but incredibly powerful relationship that connects the three most fundamental properties of any circuit you'll ever see.
Now, what I think is so cool about this graph is how it proves the law visually. See, as you increase the current that's moving to the right along the bottom, the voltage goes up in perfect proportion. It creates a perfectly straight line. And the steepness of that line, its slope, that is the resistance. So a steeper line means a higher resistance. It all just clicks.
And this slide just brilliantly shows you the two extremes. Over on the left, you've got a short circuit. The resistance is basically zero, like a massive, wide-open fire hose. On the right, you've got an open circuit. The resistance is infinite. It's like the pipe is completely blocked. No current can flow at all. All right, so we've got a handle on how a single resistor behaves. Now, let's start actually building something. The simplest way you can connect components is in series, which is really just like linking them together in one long chain.
So what's the big takeaway here? It's that single path. The current is like a train on a single track. There are no other tracks to switch to, no exits to take. It has one way to go. And because of that, the amount of current, the flow, has to be exactly the same at every single point along that path. It just has to be.
And you're going to love how easy it is to calculate the total resistance. You literally just add them up. If you have a 10 ohm resistor followed by a 30 ohm resistor in series, your total resistance is 40 ohms. It's that straightforward. Okay, let's bring in our next major rule. This one comes from Gustav Kirchhoff, and it's this incredibly powerful law of conservation. Basically, it makes sure that the energy budget in any closed-loop circuit always balances out to zero. So putting that in simpler terms, whatever amount of voltage a power source like a battery puts into the circuit has to be completely used up by all the other components in that loop. No more, no less. The books have to balance perfectly. And here it is as an equation. The sum of all the voltage drops, that's the energy being used by things like resistors, must equal the sum of all the voltage rises, the energy being supplied by the batteries. It's a perfect state of equilibrium. You know, now that we have Ohm's and Kirchhoff's laws under our belt, we can actually use them to create a super handy tool. Now, this isn't some new law of physics, but it is a really clever shortcut that engineers use all the time. It's called the voltage divider rule. The real beauty of this formula is that it lets you skip a whole step. Instead of having to calculate the total current flowing in the circuit first, you can jump straight to finding the voltage across any single resistor. And the logic is pretty simple. A resistor's share of the total voltage is directly proportional to its share of the total resistance. And this right here is the key idea to remember for voltage dividers. The bigger the resistor, the more work it does, and so the bigger the voltage drop across it. You can think of it like this. The biggest resistor in the chain always gets the biggest slice of the voltage pie. All right, we've gone over the rules. Now it's time to put them into practice and see how they all work together to figure out a real circuit. I mean, theory is great, but applying it is where the real fun begins. Okay, here's our circuit for today. We've got an 8.4 volt battery and 3 resistors all in a series, a 10 ohm, a 30 ohm, and a 100 ohm.
Our mission, should we choose to accept it, is to find the total resistance, the current flowing through it, and the voltage across each of those resistors.
All right, let's do this step by step. First up, total resistance. Since they're in series, this is the easy part. We just add them up. 10 plus 30 plus 100. That gives us a grand total of 140 ohms. Got it? Good. Step 2. Let's find the current using our old friend Ohm's law. We take the voltage, 8.4 volts, and divide it by our total resistance of 140 ohms. That comes out to 0.06 amps or 60 milliamps. Now for the last piece of the puzzle, the voltage drops. We just apply Ohm's law to each individual resistor. And here's the magic part. What happens when you add up those individual voltage drops? You've got 0.6 volts plus 1.8 volts plus 6.0 volts, and what does that equal? Exactly 8.4 volts. That's Kirchhoff's law right there in action. It all adds up perfectly.
But you know what? There's an even more satisfying way to prove we got everything right. Let's take a look at power, which is measured in watts. The power the battery supplies has to be perfectly matched by the power the resistors consume. And there it is. The battery supplies 216 milliwatts of power. And if you go and calculate the power used by each one of those resistors and add them all together, guess what? You get exactly 216 milliwatts. It's a perfect balance. It's moments like this that just show you the beautiful consistency of physics. So, let's do a quick recap. Ohm's law, V equals IR, is our foundation. For resistors in a series, the resistances just add right up. Kirchhoff's law tells us that all the voltage supplied gets used up in a closed loop. And the voltage divider rule? That's our handy shortcut for figuring out how all that voltage gets shared. So these rules we've covered, they're perfect for a single path. They explain everything flawlessly. But what happens when that path splits? What happens when the current gets to a fork in the road and suddenly has a choice of which way to go? Well, that's where things get really interesting. And it's a whole new ballgame with a whole new set of rules. For another time.